Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at proofs by contrapositive. So first we have to understand what is meant by contrapositive. So we've already seen statements of this form, A implies B. The contrapositive of that statement, you basically flip the B and A around and add these negation symbols. This says not B implies not A. These two statements here are logically equivalent. If A implies B is true, then so too is not B implies not A. Again, this statement is called the contrapositive. It's helpful in proofs because sometimes it's much easier to prove the contrapositive than to prove the implication directly. But we're going to start by writing the contrapositive of some statements. So I have a statement here, if I study hard, I will score an A in maths. So that means if A, then B. A is the condition that I study hard. B is the condition I will score an A in mathematics. So the contrapositive of this statement is not B implies not A. So the contrapositive of this statement, if I don't score an A in maths, I don't or didn't study hard. So these two statements here are logically equivalent. If the black is true, then the blue is true. Let's look at this one. If a quadrilateral has two pairs of parallel sides, then it has two pairs of equal sides. So here we have an if-then statement, a statement of the form A implies B. A is the condition that the quadrilateral has two pairs of parallel sides. B is the condition that it has two pairs of equal sides. So the contrapositive, not B, implies not A. If a quadrilateral does not have two pairs of equal sides, then it does not have two pairs of parallel sides. In blue is the contrapositive. The statement in black and statement in blue are logically equivalent. So if I don't know how to prove this statement here in black, I might have a go at proving the statement in blue because that is tantamount to the same thing in maths. Let's look at two examples where we prove the contrapositive. So here we're told that x is an integer. If 7x plus 5 is odd, then x is even. So if we're proving the contrapositive, what we want to do is update our proposition. And that will be if x is not even, so that means x is odd, because remember x is an integer here. If x is odd, then 7x plus 5 is not odd. 7x plus 5 is even. This in red is the contrapositive of our original proposition. I have flipped the two conditions and negated them. I've taken the opposite of the two original conditions and flipped them around. So if we prove what's in red, we will have proved what's in blue because these two statements are logically equivalent. So you probably know by now how we're going to start this. If we're saying that x is odd, we're going to write x equals 2k plus 1, where k is an integer. This is how we write an arbitrary odd integer. So I want to show that if x is odd, then 7x plus 5 is even. So if this is x, I'm just going to substitute this into our expression 7x plus 5. So this is 7x plus 5. Now if I expand the brackets, I get 14k plus 7 plus 5, which is equal to 14k plus 12. So I can take out a common factor here of 2. Now the thing is 7k plus 6, this thing here has to be an integer. If k is an integer, timesing it by 7 gives another integer, plusing 6 gives another integer still. This is 2 times an integer. Whenever you times 2 by an integer, you get that it is even. So we have proved that if x is odd, 7x plus 5 must be even. In proving the red, we have proved the blue because the red and the blue are logically equivalent. All right, let's look now at one more example. So here we're told that a and b are both integers, and that if a plus b is odd, then a does not equal b. We are going to prove the contrapositive. So we're going to update our proposition. We're going to switch and negate the two conditions. So the opposite of a does not equal b means a equals b. If this is not true, then this is true. A plus b is odd because a and b are integers. That will mean the opposite of that is a plus b is even. So this is actually super easy to prove. If a equals b, then a plus b is just a plus a, which is 2a. Now, because a is an integer, this is 2 times an integer. This is 2 times a whole number, so that means it must be an even integer. So I've got to be honest, the original proposition would not have been hard at all to prove, but look how easy it was to prove the contrapositive. Sometimes it's easier to prove the contrapositive. Now, because we've proved the red and because these two statements here are logically equivalent, we have proved our proposition. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.